Okay, 3.4, exponential and logarithmic equations. An exponential equation is an equation containing a variable in an exponent. Solving exponential equations by expressing, we will solve exponential equations by expressing each side as a power of the same base. And once we have that, we can equate the exponents. For instance, all right, in the first example, we want to solve 5 to the 3x minus 6 is equal to 125. So let's rewrite the steps. So we're going to first rewrite the equation in the form b to the m is equal to b to the n. All right, so let's do that. So we have 3x to the 5 raised to the 3x minus 6 is equal to 5 cubed. Now that we have the same base, we can equate the exponents. In other words, we can say that m is equal to n. So in this case, we have 3x minus 6 is equal to 3. All right, now let's solve for the indicated variable. Let's solve for x. So we have 3x is equal to 6 plus 3. So 3x is equal to 9. Dividing by 3, we get that x is equal to 3. Let's consider another example. Let's solve the exponential equation. 8 to the x plus 2 is equal to 4 to the x minus 3. All right, so we want to rewrite the equation having the same base on both sides. So what do we have here? 8 can be written as 2 cubed and times x plus 2. 4 can be written as 2 squared times x minus 3. So we have, now we can equate the exponents. So we have 3 times x plus 2 is equal to 2 times x minus 3, which is 3x plus 6 is equal to 2x minus 6. Solving for x, we have 3x minus 2x is x, and a negative 6 minus 6. So therefore, x is equal to a negative 12. Let's continue with solving exponential equations. In these examples, we will use logarithms to solve the exponential equation. So the first thing we want to do is to isolate the exponential expression. Isolate it on one side of the equation. And then we're going to take the common logarithm on both sides of the equation for base 10. And we're going to take the natural logarithm on both sides of the equation for bases other than 10, and use the appropriate property of logarithms to simplify. All right, so in the first example, we have 5 to the x is equal to 134. All right, so this is a base other than 10, so we're going to take the natural log of both sides of this equation. So the natural log of 5x is equal to the natural log of 134. All right, and we know that this is x times the natural log of 5 is equal to the natural log of 134. Solving for x, we have x is equal to the natural log of 134 divided by the natural log of 5. And if you use your calculator, x is approximately 3.04. In the next example, let's solve the exponential equation. 10 to the x is equal to 8,000. Base 10, so we're going to take the common log of both sides of this equation. So that's the log of 10 to the x is equal to the log of 8,000. Right? So this is x times the log of 10 is equal to the log of 8,000. The log of 10 to the base 10, of course, this is going to be 1. So that's x times 1 is equal to the log of 8,000. So we have x is equal to the log of 8,000. All right, if you use your calculator to get an approximation, so x is approximately 3.9. In the next example, let's solve the exponential equation. 7 times e to the 2x minus 5 is equal to 58. So the first thing we need to do is to isolate the term involving the exponent on one side of the equation. So we're going to isolate the exponential expression here. So we have 7e to the 2x is equal to 58 plus 5. So 7e to the 2x is equal to 63. Or we can say that e to the 2x is 63 divided by 7 is 9. Now we have an exponential equation. E to the 2x is equal to 9. That can be solved. We see that the base is e. So the next step is to take the natural log of both sides of the equation. So we have the natural log of e to the 2x is equal to the natural log of 9. So what do we have? We have 2x multiplying by the exponent. 2x times the natural log of e is equal to the natural log of 9. The natural log of e is 1, so we have 2 times 1, 2x times 1, which is 2x, is equal to the natural log of 9. Solving for x, we have x is equal to the natural log of 9 divided by 2. Or, if you use your calculator to get a numerical approximation, this is approximately the natural log of 9 divided by 2 is approximately 1.10. In the next example, we will solve the exponential equation 3 to the 2x minus 1 is equal to 7 to the x plus 1. So we're going to take the natural log of both sides. So we have the natural log of 3 to the 2x minus 1 is equal to the natural log of 7 to the x plus 1. All right? Using the properties of logarithms, we can multiply by the exponent. So we have 2x minus 1 times the natural log of 3 is equal to x plus 1 times the natural log of 7. All right, let's simplify by doing the multiplication. 2x times the natural log of 3 is 2x times the natural log of 3 minus the natural log of 3 is equal to x plus 1 times the natural log of 7. X times the natural log of 7 is x times the natural log of 7. And 1 times the natural log of 7 is going to be plus the natural log of 7. All right? Now, what we'd like to do now is to put all of the terms involving the variable x, the unknown, on one side of the equation. So we have 2x times the natural log of 3. The x times the natural log of 7 must be transposed from the right to the left-hand side of the equation. So we have minus x times the natural log of 7 is equal to the natural log of 7 plus the natural log of 3. And now we're going to factor out the x here. We have x times 2 times the natural log of 3 minus the natural log of 7 is equal to, on the right-hand side of the equation, the natural log of 7 plus the natural log of 3. All right, solving for x, we need to now divide both sides by 2 times the natural log of 3 minus the natural log of 7. So we have the natural log of 7 plus the natural log of 3 divided by 2 times the natural log of 3 minus the natural log of 7. All right, and again, if you use your calculators, you can obtain a numerical approximation. The approximation is roughly 12.11. The next exponential equation that we wish to solve is e raised to the 2x minus 8 times e to the x plus 7 is equal to 0. If we look at this exponential equation, we see that it is quadratic in form. In other words, if you let u be e to the x, then we can express this equation as u squared minus 8u plus 7 is equal to 0. And here we have a quadratic equation which can be solved by factoring. So let's see how this applies to the given equation. So if we factor this equation, e to the 2x can be factored as e to the x times e to the x. And then plus 7 minus 1. So we see that we have the factors of the original exponential equation. So now we can use the zero product principle to solve the equation. So we have e to the x minus 7 is equal to 0, or we have e to the x minus 1 is equal to 0. And now solving each equation separately, we have what? E to the x is equal to 7. Base e So we're going to take the natural log of both sides of the equation. So the natural log of e to the x is equal to the natural log of 7. And what do we have? X multiplying by the exponent. We have x times the natural log of e is equal to the natural log of 7. The natural log of e is 1, so we have x times 1, which is x, so x is equal to the natural log of 7. All right? In the next exponential equation, we have e to the x minus 1 is equal to x. Let's solve. E to the x is equal to 1. Let's take the natural log of both sides, so that's the natural log of e to the x is equal to the natural log of 1. All right, so this is x time multiplying by the exponent x. This is x times the natural log of e is equal to the natural log of 1. The natural log of e is 1, so we have x times 1, which is x. So x is equal to the natural log of 1. If we want to go another step, the natural log of 1 is what? Is 0, because e to the 0 is 1. So the solution set consists of 0 and the natural log of 7. If you like, you may use your calculator. 0 and the natural log of 7 is approximately 1.95. Now, let's look at what it means to solve logarithmic equations. A logarithmic equation is an equation containing a variable in a logarithmic expression. All right, and to solve these logarithmic equations, we will use the definition of a logarithm. So what we really want to do initially is to express the equation in the form the log of m to the base b is equal to c. And once we do that, we can then use the definition of the logarithm to rewrite the logarithmic equation in exponential form. In other words, we know that the log of m to the base b is equal to c is equivalent to b to the c is equal to m. And then once we get the equation in this form, we solve for the indicated variable. And the last step you might want to do is just check your result. All right, so let's solve. So the first equation, the logarithmic equation to be solved, is the log of x minus 4 to the base 2 is equal to 3. All right, so we first want to express the equation in the form, it's already in the form the log of x minus 4 to the base 2 is equal to 3. So it's already expressed in logarithmic form here. All right, so let's see what this means. If we use the definition of the logarithm, this is going to be 2 cubed is equal to x minus 4. All right, so now we can solve this equation. 2 cubed is 8. 8 is equal to x minus 4. So therefore, 8 plus 4 is equal to x. So x is equal to 12. All right. All right, let's check it. Let's check to make sure that this is a good solution or a solution. So to check, we go back to the original equation. And what do we have? The log of 2. X is 12, so that's 12 minus 4 is equal to 3. Let's see. So what do we have here? We have the log of 12 minus 4 is 8 to the base 2. Is that 3? Well, the log of 8 to the base 2 is indeed what? 3, because 2 cubed is 8, so therefore 3 is equal to 3, and it checks out. All right? In the next example, let's solve the logarithmic equation. 4 times the natural log of 3x is equal to 8. All right, so let's first put it in the appropriate form. The natural log of 3x is equal to, dividing both sides by 4, we get the natural log of 3x is equal to 2. All right? So now we can rewrite this in exponential form. So what do we have? We have e to the natural log of 3x is equal to e squared. So we have the natural log, so we can multiply. So what do we have? We have the natural log of 3x is 3x. E, you recall the property that e raised to the natural log of 3x, again the base is e, so we get 3x is equal to e squared. And now x, dividing by 3, we get e squared divided by 3. So x is equal to e squared divided by 3, or if you use your calculator, you should get the approximation. X is approximately 2.46. All right. Another example of solving a logarithmic equation. All right, so the first thing, we want to write this as the log of a single expression. So since we're adding to log, if we use the product rule in reverse, we have that this is the log of x times x minus 3 is equal to 1. All right, and since we have the common log, in other words, base 10, all right, so we can rewrite this in exponential form as 10 to the first is equal to x times x minus 3, just using the definition of a logarithm. Now let's simplify. We have 10 is equal to x times x is x squared, and x times a negative 3 is a negative 3x. So we have 0 is equal to x squared minus 3x minus 10. All right, let's solve this quadratic equation. Let's see, does it factor? I think so. It does factor. So we have 0 is equal to x minus 5 times x plus 2. And now using the zero product principle, x minus 5 is equal to 0, or x plus 2 is equal to 0. So we get x is equal to 5, or x is equal to minus 2. All right, let's check. All right, let's check. All right. Let's check when x is equal to 5. All right, when x is equal to 5, we have what? The log of 5 plus the log of 5 minus 3 is equal to 1. So we have the log of 5 plus the log of 2 is equal to 1. And again, using the inverse of the product rule, we can rewrite this as the log of 5 times 2, which is equal to 1. So the log of 5 times 2 is the log of 10 is equal to 1. All right? And the log of 10 again, since this is base 10, we have 10 to the 1 is equal to 10, so it checks out. 1 is equal to 1. So 5 is a solution. All right, let's check now. All right, when x is equal to minus 2. All right, checking. So we have the log of a negative 2 plus the log of a negative 2 minus 3 is equal to 1. All right, already this is a flag. You cannot take the log of a negative number. Negative numbers do not have logarithms. All right, so we can conclude that a negative 2 is not a solution. So the solution set is just a set containing 5. All right, we have another logarithmic equation to solve here. All right, so first let's rewrite the natural log of x minus 3. And now using the reverse of the quotient rule, I'm going to have the natural log of 7x minus 23 divided by x plus 1. All right, so we have the natural log of one side is equal to the natural log of the other side. So therefore that we can equate m and n, so to speak. So x minus 3 is equal to 7x minus 23 divided by x plus 1. So now we want to solve this equation for x. So let's multiply both sides by x plus 1. So we have x minus 1 times x plus 1 times x minus 3 is equal to 7x minus 3 divided by x plus 1 times x plus 1. The x plus 1s will cancel, leaving you with 7x minus 23. All right, let's simplify by performing the indicated multiplication here. So what do we get? We get x squared, positive 1x with a minus 3x. So the middle term is a negative 2x minus 3 is equal to 7x minus 23. Combining like terms, we have x squared. So we have a minus 2x. If we bring the 7x from the right to the left-hand side, we have a minus 2x minus 7x minus 3. A negative 23, when transposed to the left-hand side of the equation, we get a positive 23 is equal to 0. All right, so we have x squared minus 2x minus 7x is a negative 9x. A negative 3 plus 23 is a positive 20 is equal to 0. Now we have a quadratic equation. Does it factor? Yes. So if we factor the quadratic equation, we have x minus 4 times x minus 5. Now if we use the zero product principle, setting each factor equal to 0, and then solving each equation separately, we have x is equal to 4 and x is equal to 5. And if you check, both 4 and 5 will produce a true statement. So the solution set consists of the elements 4 and 5.